Hello everyone, welcome to this video. In this video, we're going to talk about restoring division algorithm. This video is a continuation of our computer architecture lectures. If you haven't gone through our computer architecture playlist, I'll keep a link on top of the video and then you can check that playlist out. Now let's get back to the topic. So restoring division algorithm is one of the approach on how computer performs division. So let's take a simple example and then understand this particular flowchart with that particular example. Suppose we want to do 11 divided by 4. So basically in this particular problem, what we have terminology dividend, which is 11, and our divisor is equal to 4. So let us refer to our dividend as Q. The binary representation of our dividend is going to be 8 1 2 4 8. So 8 to 10 plus 1 equal to 11, and then the divisor 4 is going to be represented in bit 1 0 0, but the number of bits that we're going to place in the divisor represented by B is going to be one digit or one bit greater than the number of bits in Q. So let's start our task. First of all, we'll create a table. We will have our operations, and after that we will have the value of A. So if you see here, the value of A must be initialized as 0. So the number of bits we're going to use to initialize the value of A as 0 is the number of bits in Q plus 1. Similarly, we have a Q bit. We have Q bit as 1011. 1011. Now okay, the flowchart says that we represent this with M. I'm going to use the consistent notation here. So this particular divisor is going to be represented by M, but what we actually want is we also want to find out M complement. So the M complement of this is 11011, and then M complement plus 1 is going to be, if we add 1 to this, then this is going to be 0 0 1 1 1. So we'll have M complement plus 1 equals to 11100. We have our divisor and our dividend. So now what do? We also initialize the value of n, and that particular value of n is going to be equal to the number of bits in Q, which is 4. Proceeding down, we have shift left AQ. So we're going to take this AQ value in a combined manner and then shift left to it. So 1 is going to be placed here. We don't know what value will occur here, so we'll leave it blank. This particular one will go here, this 0 will go here, and this one will come here. The rest of the values are all 0, so we can just write zeros. This was our initialization part. So in the second step, we did shift left AQ, and then we actually don't know what this particular last bit is. What we do after this is we perform A minus M. So basically A minus M is equivalent to A plus M complement plus 1. We already have M complement plus 1, so we're going to basically add this. So A equal to A minus M. So we're going to add M complement plus 1, 11100. If we add this, what we get is 10111. Now what we do is we check the sign bit of A. So basically if this is A, the sign bit of A is 1. Now if the sign bit of A is 1, what it says is that the value that we've left empty here should be 0. So 0 1 1, and then we'll fill the empty value 0 here. Also, we are asked to restore A, which means we are asked to go to the previous value of A, disregarding what the result of A minus M is. So basically we perform 0 0 0 0 1. We basically do a restore operation, and then the remaining value is going to be the same. After that we decrease n is going to be 3, and then we check if the value of n is 0 or not. Since the value of n is not 0, so we go back to the flowchart again and then shift left AQ. So one iteration of this particular operation is complete. Let's head back to shifting left AQ again. If you see here, this 0 is going to come here, the last value is unknown. 1 will come here, 1 will come here, 0 will come here, 1 will come here, and then the remaining bits are all 0. Now what we do is we again do a equal to a minus m. So we'll be adding this value here, 1 1 1 0 0. Once we add this, we'll get the result 0 1 1 1 1 and 1 1 0, and then we don't know the value of this one here. So what we get here is the value 1, which means if we check the sign bit of a, we see that our q0 should be 0, and then we again should restore the value of a, which means we are going to restore this particular value here, 0 0 0 1 0, and then we decrement our n, which means the n value of n is going to go to 2 and the remaining q is going to stay the same. I'll also write what I performed here. I performed a restore operation. Again, since the value of n is not 0 yet, so we again go back and then we shift left. We perform shift left operation for AQ. So now our shift left operation is going to be give 1 0 0 empty space 1 0 1, and then the remaining values are going to be 0. Now we are again going to add m complement plus 1 here, so we'll do a minus m. Okay, so 1 1 1 0 0, we'll add this. The result we get is 1 plus 0 is 1, 0 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1. Now since this is a subtraction operation, so there should not be a carry, so we disregard this particular carry here. Once we get the sign of a as 0, what we do is we place 1 at the end. So 1 0 0, and then we place 1 at the end. And if you see, we don't need to restore the value of a once the sign bit of a is equal to 0. So we directly decrement our counter and then we move to the next iteration. Since the value of n is still non-zero, so we again perform shift left AQ. Now we're going to shift this 0 0 0 1 1 0 0 1, and then empty space here. We are again going to add 1 1. What are we supposed to add? 1 1 1 0 0 1 1 1 0 0, which means we performed a minus m here. The result is 1 1 1 1 1. Since the sign bit is 1, so we need to place a value 0 here, and also we need to restore our old value of a, which means this is 0 0 0 1 1, and then the q remains the same. Now our step counter is 0. Once our step counter is 0 or n is 0, then we stop the operation. Now the result that we see, the value of a is our remainder, and then the value of q is our quotient. So remainder is equals to 1 2 3 here, and then the quotient is equals to 2. So 4 into 2 plus 3 is equivalent to 11. Hence we got a correct answer. So this is how you perform restoring division algorithm. If you have any confusion or if you did not understand any steps, feel free to comment down and I'll try to help you out. You can take some new values, like you can try some values like 22 divided by 5 and check out if you get the correct answer. Do comment down if you got the concept and answer right. So that's all for this video. Hopefully the concept is clear to you, and then the flowchart is also clear to you. I'll come up with another video for non-restoring division algorithm. If you like our content, do like our video and share it among your friends so that everyone can understand this particular concept in computer architecture better. Also, don't forget to subscribe to our channel and hit the bell icon so that you don't miss any updates. We continuously post new videos on our channel. Now, I'll see you in the upcoming video where I'm going to post about non-restoring division algorithm with an example. Until then, bye-bye.